All right, it is day 7. Let's just get started. All right, day 7, no space left on device. You can hear birds chirping and raindrops hitting leaves as the expedition proceeds. Occasionally, you can even hear much louder sounds in the distance. How big do the animals get out here anyway? The device the elves gave you has problems with more than just its communication system. You try to run a system update. System update, dash dash please, dash dash, pretty please with sugar on top, and no space left on device. Perhaps you can delete some files to make space for the update. You browse around the file system to assess the situation and save the resulting terminal output, which is your puzzle input. For example, then we can see, you start by going to the root directory, listing, and you sort of see a directory and some files and whatever. The file system consists of a tree of files, plain data, and directories which can contain other directories of files. The outermost directory is called slash, or root. You can navigate around the file system, moving into or out of directories and listing the contents of the directory you're currently in. Within the terminal output, lines that begin with a $sign or commands you executed, very much like some modern computers. CD means change directory. This changes which directory is the current directory, but the specific result depends on the argument. CD X moves in one level. It looks in the current directory for the directory named X and makes it the current directory. CD ... moves out one level. It finds the directory that contains the current directory and then makes that directory the current directory. And CD/ switches the current directory to the outermost directory, just called slash or root sometimes. ls means list. It prints out all the files and directories immediately contained by the current directory. 123 ABC means that the current directory contains a file named ABC with size 123. dir xyz means that the current directory contains a directory named xyz. Excuse me. Given the commands and output in the example above, you can determine that the file system looks visually like this. Here, there are 4 directories: slash, the outermost directory, A and D, which are in slash, and E, which is in A. These directories also contain files of various sizes. Since the disk is full, your first step should probably be to find directories that are good candidates for deletion. To do this, you need to determine the total size of each directory. The total size of a directory is the sum of the sizes of the files it contains, directly or indirectly. Directories themselves do not count as having any intrinsic size. The total sizes of the directories above can be found as follows. The total size of directory E is 484 because it contains a single file I of size 584 and no other directories. And you see we have... Oh, there it is. Couldn't find it. Yep, it's right there. Single file called I, which is of size 584. Cool. Directory A has a total size of 94,853 because it contains files f, g, and h.lst, plus file I indirectly because directory A contains directory E, which contains I. We can see it all up there. I'm not gonna add those up. I'm sure it's right. Directory D has a total size of 24,933,642 bytes. Presumably bytes. As the outermost directory, slash contains every file. Its total size is a lot. The sum of the size of every file. To begin, find all the directories with a total size of at most 100,000, then calculate the sum of their total size. In the example above, these directories are A and E. The sum of their total sizes is 95,437. As in this example, this process can count files more than once. What that means is that what it says, right? Find all of the directories with a total size of at most 100,000. What is the sum of the total sizes of those directories? Okay, so once again, Let's take a look. Okay, so first off, well, no. Very first thing we do every time, let's just minimize this, is to fill in the sample input and put in the expected result in the tests. So, yeah, so we load in all the lines from the file, and then we parse the directory structure. At first, it was all just in one long, impossible to understand function, but I moved it into a separate function because we need it in part B as well. Anyway, so the parse directory structure is a big chunk of what we need to do here. So I don't know why I did this. There's no reason to be that thorough, but when a parser, it's the initial state for this parser was just unknown. And I knew that was safe because the very first thing we see is the $sign, and that means that we're parsing a command line. I'm being very explicit here because, well, so that it's more readable, and so that I didn't lose my way when I was trying to do this, on a timer as I did last night. Anyway, so we know that we're looking at a command line, and then we make sure that the first character is a $. Otherwise, we've messed up somewhere. And then we create the command line variable based on the line, ignoring the first two characters, and that gives us an argument vector. The first part of the argument vector is the command that we're running, and if that is cd and the argument is /, then we set the current directory to the root directory, which I will get back to in a little bit. If we saw a path that wasn't just / but started with a /, we would need to do something special with that. I didn't know if we were gonna, so I just put in assert false so that if that happened, the tests would fail or something would happen, so I knew that there was a problem somewhere. This handles the cd ... which moves us into the parent directory, and if none of those match, that means that we're going into another subdirectory, which is what happens right here. Cool. Otherwise, if it's not cd, if it's ls, then we are listing, and then we change the state of our parser to be list. And then we continue, so we go on to the next line. Let me open this right next to it so we can see what's going on. Yep, cd and then ls. So yeah, seeing the ls puts us into the list state for the parser, and it splits by space. Oh yeah, never mind. Yep, splits by space, and if we assume that size and name, but if size actually says dir, then we create that directory in our we add that to the list of directories that we know exist. If it's a file, then we store the size and the name in the current directory. And and that explains how we handle this line, this line, this line, and this line. And then as soon as we see this $sign, that tells the parser that we are back at a new command line. And then that's what happens here. And rinse and repeat. Cool. Okay. So Um, I'm sure that you can that you could do this much more efficiently. But I ended up implementing a directory structure thing, which is what we have here. So a directory class, which has 3 attributes, some subdirectories and files, and a parent directory. And they have the add file and add directory methods that we saw in the parser. Then there is a total method. Terrible name. I should have changed that before I recorded this, but here we are. Total returns the total size of every file contained directly or indirectly in this given directory. So it goes through the subdirectories and gets their totals and adds it to the total. Then it goes through all the files and adds their sizes to the total and returns total. Boom. So far, so good. Our specific task was to, let me see if I forgot. Okay, find all the directories with a total size of at most 100,000. So, let's go down to part A again. So we parsed the directory structure. Oh, sorry, I should do this first. So I created a directory and called it root. And I keep that as a global variable because being able to just always jump down back to the root directory is pretty handy. And I needed an anchor anyway, right? So it's all good. Okay, so we parsed the directory structure and we set the current directory to be root. That's entirely unnecessary, but it's there. So then man, that explains a lot. I'm missing an L right there. Okay, well, okay. So I knew that I needed to go through all the subdirectories and calculate their size. So I added a walk subdirectories method, which is a very common thing to have. So you can walk through a directory structure and apply a function to every directory entry. So files, directories, devices, whatever, right? And walk subdirectories is very simple. It takes the function, it calls the function on itself, and then it calls walk subdirectories on all of its subdirectories passing in the same function. So in order to keep track of that, I created this global variable and I put global, in here. This tells it that, whenever I'm referring to a method, a variable called total size of directories under 100,000, that it's the global one. I'm not trying to define a new variable with that same name in this function. So I get the total, and if the total is less than 100,000, then I add that to this variable. And yeah, and just to be clear, the thing it talked about in the puzzle with that a file can be counted more than once is because when you look at a file that is both in this E directory, oh, it's easier to look at it over here. Yeah, so I is going to be counted both when we get the total for E and for A, and so on and so on. So that's why it might get counted twice. But that's what we do. We add total size to that, and then we return it, and boom, that was part A. Not too bad. Part 2. Okay. Now you're ready to choose a directory to delete. Now you are ready to choose a directory to delete. The total disk space available to the file system is 70 million. They could have really put some dots or something in there. 70 million. Yep. 70 million. To run the update, you need unused space of at least 30 million. You need to find a directory you can delete that will free up enough space to run the update. In the example above, the total size of the outermost directory, and thus the total amount of used space, is a very large number. This means that the size of the unused space must currently be another not quite as large number, which isn't quite the 330 million required by the update. Therefore, the update still requires a directory with total size of at least 8 million something to be deleted before it can be run. And yeah, it goes into a lot of detail here. Point is, we need to find the smallest directory that is larger than what we need. And I gotta tell you, this seems like a pretty simple bit of arithmetic, but it took me a while, and I ended up having to use my whiteboard to kind of put some stuff up there to figure it out. So I had 5 variables to keep track of this. So what's the total capacity, the used capacity, the available capacity, how much capacity is needed, and what's the difference between what we need and what we have, and it was crazy. But this is the really brief version of it. So no real surprises here. It's very much the same pattern as in part A. We parse the directory structure, we create something to track it, we create a function that we can use to walk the subdirectories. In this case, it is an array of just all the directory sizes that we've seen. We don't. The answer that we're looking for is just the size of the smallest directory greater than what it needs to be, which is use capacity minus 40 million. So yep, after you're done walking subdirectories, dir sizes contains just all the different sizes. Then we sort it, and we just go through them until we find one that's greater than this, return it, and boom, that's it. Let's see, is there anything else we didn't cover? Nope, I think that's about it. Yeah. Let me know if you have any questions. Otherwise, just like and subscribe.